An earthquake on the Solitario Canyon Fault generates near-field velocity pulses that hit 2.5 g of peak acceleration at a depth of 300 meters. That specific kinetic load exceeds the plastic deformation limit of yieldable steel arch sets. The resulting structural shearing collapses the walls, mechanically isolating the internal storage vaults from the surface. To understand this failure, we examine the host rock's micro-scale petrography. The reality is a system already pre-loaded with extreme lithostatic pressures. The surface geology of Yucca Mountain presents as a stable desert environment, but deep within the structural block, core samples expose cooling joint density variations. The rock is not a uniform solid, it is heavily fractured. This diagram maps the TMHC feedback loop: thermal, mechanical, hydrological, and geochemical dynamics. Introducing nuclear waste creates a thermal load, altering in situ stress and expanding fracture networks. This mechanical shift triggers a hydrological geochemical reaction, dissolving the rock matrix and creating new fluid pathways. The repository actively degrades its own structural integrity. Because of these constant thermodynamic feedbacks, traditional static rock mass classification systems failed to predict how the facility will behave over a 10,000-year design life. The initial subsurface construction phase began at the Exploratory Studies Facility North Portal. On September 23, 1994, crews deployed the Jarva Mk-27 tunnel boring machine, a 7.62-meter diameter designated the Yucca Mountain Express. By April 12, 1995, the machine reached a depth of 200 meters, penetrating the welded Topopah Spring tuff horizon. On May 14, 1996, the excavation encountered severe conditions. The official log notes, TDM excavates through the active Bow Ridge fault zone, where downhole strain gauge telemetry reveals microseismic activity and elevated fracture permeability. This unexpected geomechanical threat forced engineers to install heavy yieldable steel sets to stabilize the tunnel. Researchers are now running ensemble machine learning algorithms, like XGBoost and Random Forest, to retroactively analyze that historical operational data. This decision tree matrix maps the raw telemetry against actual rock mass quality outputs. The models evaluate real-time response parameters, specifically torque and thrust, to calculate the TBM net penetration rate. By mapping these parameters into a combined jamming risk scoring system, the algorithms can identify potential machine jamming events caused by geological anomalies. The most heavily funded geotechnical project in history generated the precise telemetry data required to retroactively detect the geological hazards that original engineering models failed to anticipate. A deeper audit requires looking at the specific lateral excavations branching off the primary 8-kilometer loop, specifically a sector known as Drift Alcove 5. This 2D stress tensor map of Alcove 5 isolates anomaly alpha. The in-situ stress-strain telemetry registered a horizontal stress anisotropy ratio of K0 equals 1.35. The standard regional geomechanical norm sits between 0.55 and 0.72. The telemetry recorded values more than double that baseline. Physically, this localized stress concentration operates as a continuous shear force acting on the tunnel floor. This localized stress concentration aligns with the expected mechanics of an unmapped, deep-seated blind thrust fault intersecting the main excavation loop. Because the repository stability models were mapped against regional averages, the engineering framework did not account for localized anisotropic shear forces capable of compromising the containment infrastructure. The forensic audit also extends to hydrological containment, utilizing high-precision mass spectrometry taken from deep drill holes. This data plot illustrates anomaly beta. It charts localized spikes of chlorine 36 to chlorine ratios, exceeding 1,200 times 10 to the negative 15. These isotopic spikes occurred at the exact spatial coordinates of 36 degrees 51 minutes 21 seconds north by 116 degrees 25 minutes 35 seconds west, within the fault splays of the facility. This discovery challenges the predicted vadose zone flow models, which rely on capillary-driven matrix imbibition, the slow absorption of water through porous rock, to achieve fluid isolation. The standard fluid flow equations assume that liquid front advancement, denoted as x, scales as a function of the square root of time. The isotopic data reveals that long-term average flows were operating 10 times faster than the modeled matrix imbibition allowed. This hypervelocity vertical migration indicates the presence of continuous open vertical fracture corridors reaching from the surface to the storage vaults. The presence of meteoric chlorine-36 at depth indicates that the site lacks the intended hydrological isolation, establishing a high-speed conduit between the radioactive waste and the biosphere. We have to evaluate the Subterranean High Storm 100 system, vertical and horizontal vault architectures, which are designed to house the dual-purpose canisters of spent nuclear fuel. The material defenses of these cavern vaults rely on steel-lined cavities, surrounded by low permeability, compacted swelling clay buffers intended to block moisture. This table outlines the official performance allocation for this disposal concept. Scrutinizing the waste form baseline metric, the model assumes a fractional degradation rate of exactly 2 × 10⁻⁵ per year. The buffer materials are sheathed in metal capsules, meant to survive a 100-year pre-closure operational period. After that, the system is expected to maintain isolation for 10,000 years. The multi-barrier containment strategy relies on these engineered materials decaying at a predictable baseline. It offers no recorded resistance against a high-energy geological intrusion. This brings us to the final cataclysmic edge case, a mantle-derived basaltic dike intruding through the Yucca Mountain block and intersecting the subterranean vaults. The system absorbs a massive thermal shock, with temperatures exceeding 1,100 degrees Celsius. Secondary to the heat is the kinetic force. Volcanic gas pressurization exceeding 15 megapascals impacts the subterranean structural framing. The extreme heat gradient forces rapid expansion of moisture within the rock matrix, leading to the structural disintegration of the cavern walls. At 1,100 degrees Celsius, an immediate geochemical feedback occurs. The retrograde solubility of calcite reverses against the prograde solubility of silica, destabilizing the host rock's molecular integrity. The structural liners fail under the thermal load, and the shockwave mitigation framing loses mechanical integrity. As the internal thermal and pressure thresholds are breached, the fractional degradation rate accelerates from 2 × 10⁻⁵ to a complete containment failure within a matter of